All right, we're going to do a quick overview of Kepler's laws. There's 3 of them. All right, so the first one says that orbiting objects, and you can think about like the sun and the planets or the moon and Earth, something like that, where there's something orbiting due to gravity. The orbiting objects follow a path that makes an ellipse. Now, they can be circular, exactly, or they can be slightly, elliptical, or they can be very elliptical, okay? Gravity allows for this type of orbit. Now, there's a couple points of interest in this orbit. So here I have the sun in red and the Earth in green here going around. Our orbit is much more circular, but I've exaggerated it here. And what you'll see is I have 2 dots here. One, this red dot, you can see pretty clearly, is the sun. That's at one of the foci of the ellipse. The other foci, there's nothing at it. Okay? Also, there is a point that's the closest to the sun and a point that's furthest away from the sun, or for the moon's orbit, closest to Earth, furthest from Earth. These points have the prefix peri for the close, ap for away. Ap away, think about that to remember which is which. A, ap away, A away. All right, so these points also have something else that's special about them. At this point, you'll notice that the velocity is perpendicular to the radius. That's going to be helpful because at the aphelion, if we're talking about the sun, and the perihelion, our angular velocity at that point is the radius times the speed. We don't have to find the perpendicular components of anything. Okay? If it is closest to the sun, it's perihelion. Aphelion's furthest away from the sun. If we're talking about the Earth and maybe the moon's orbit, it would be perigee and apogee. Okay? And those, that second half of the word there comes from what it's being orbited. All right, our second law says that equal areas and equal times. So if I draw a line between the sun and, say, the Earth, and I think about how much area does that line sweep out as the Earth goes for some amount of time, it's going to be equal at all points in the orbit. So if I take, for instance, maybe 1 month, this is how far it goes, and another 1 month, that's how far it goes. Those areas are going to be equal. Now, what this really is this is a conservation of angular momentum. Okay? Also, how that kind of plays out is the closer you are to the sun, the faster you're going. The further away, the slower you go. Okay? So you go slow, but that area is still the same. Okay? So what you can say is your maximum orbital speed occurs at the perihelion, and your minimum occurs at aphelion. I do have another video linked down below that goes through how we can use this conservation of angular momentum, Kepler's second law, along with the conservation of mechanical energy to solve some problems. The third law says that whenever anything's orbiting a comet, so for instance, all of the planets orbit the sun. So if I take their period squared divided by their semi-major axes cubed, I'm going to get the same number for all of the planets because they all orbit a common object, the sun. Or maybe I take all the moons of Jupiter, I can take their period squared divided by their semi-major axis cubed, and I can figure out they're all going to have the same number. What's nice here is I can use, say, one that I know really well, and I can then use the period of another one that maybe I don't know its distance, and I can predict that distance. Okay? All right, just some clarification here. So when we're talking about a semi-major axis, what that is if I take the distance from the perihelion to the aphelion and I divide by 2, that gives me the semi-major axes. If I take it between these two, the shorter edge of my ellipse, this is called the semi-minor axes. So yeah, how you would get that semi-major axes is you take the closest distance and the furthest distance, add them together, divide by 2.